The real reason trains haul empty cars across the country isn't laziness, poor planning, or wasted capacity. It's that removing a single empty car can cost a railroad far more than dragging it 1,000 miles. Across North America, empty cars account for more than a third of all the miles freight equipment travels every year, a staggering amount of apparent waste rolling down the tracks. But every one of those empty cars is there because of a chain of decisions involving a 150-year-old braking system, the physics of stopping a mile-long train, and a federal law that makes just dropping it off surprisingly expensive. Once you see how those forces lock together, the empty car stops looking like a mistake and starts looking like the smartest move on the table. To understand it, you have to start with something that happens every single time a freight train slows down, and it's stranger than most people imagine. When the engineer applies the brakes, the command doesn't reach the whole train at once. It travels as a wave of falling air pressure down a steel pipe that runs the entire length of the consist, and that wave moves at a fixed speed, roughly 400 to 600 feet per second in a normal application, a bit faster in an emergency. That sounds instant until you remember a modern freight train can stretch 1.5 miles or more. On a train that long, the rear cars don't even know the brakes are on until something like 15 to 20 seconds after the front does. Picture turning off a garden hose at the spigot and watching the far end keep dribbling for a moment before it finally stops. The flow doesn't halt everywhere at once. It tapers off, with a delay that grows the farther you are from the valve. A freight train's brakes work on the same principle, and that delay isn't a flaw anyone forgot to fix. It is just what happens when you try to send a signal through hundreds of feet of compressed air. So the front of the train begins slowing while the back is still rolling at full speed, and for a few seconds the whole machine is fighting itself. The cars up front bunch together under compression, while the cars behind stretch the couplers tight. Railroaders have names for these two forces: buff, the squeeze, and draft, the pull. Now here's where the empty car earns its place. A loaded car might weigh close to 140 tons. An empty one is a fraction of that. When the same brake force hits a light car, its wheels grab much harder and faster relative to its weight, because there's so little mass holding it to its momentum. So, in a train mixing heavy and light cars, the empties react first and the loads react last. And that mismatch is exactly what turns ordinary slack action into something dangerous. Imagine loaded tank cars up front and a nearly empty car at the rear. As the brakes apply, the heavy cars resist, while the empty car bites down hard and early, sending a violent jolt of tension racing through the couplers, the train quite literally trying to tear itself apart from the inside. Release the brakes and the forces reverse, slamming the cars back together. Either way, you risk snapped couplers, or at the worst, a derailment. The obvious fix: just add more braking hardware to the empties, or sort every car by weight. Falls apart fast, because how any one car behaves depends on the entire makeup of the train, not just its own equipment. No single tweak can guarantee even forces across 1.5 miles of steel. So why not redesign the whole braking system to fix this once and for all? That question runs straight into the second reason: a piece of engineering history that has shaped this industry for over a century. Back in 1869, George Westinghouse patented the automatic air brake, and it changed everything. Before it, railroads were a chaos of hand-operated brakes and incompatible hardware. Westinghouse replaced that mess with one continent-wide standard: a continuous air pipe linking every car, so a brake command would reach the whole train through the same system, no matter who built the car or where it was going. Over the decades, the industry codified this into an ironclad rule. Every freight car and locomotive in North America had to use the same pneumatic brake setup and the same coupler. That standard was a quiet miracle of logistics. It meant a train could be assembled from cars owned by dozens of different companies, handed off between competing railroads at interchange points, and run thousands of miles without anyone stopping to swap out adapters or reconfigure equipment. Maintenance crews learned one system, spare parts inventories shrank. Any car could roll anywhere on the network. For the railroads, compatibility and simplicity beat the theoretical gains of optimizing each car for its own weight. But a universal standard comes with a trap built in. Once the entire continent runs on one system, any improvement, no matter how brilliant, has to work everywhere, for everyone, all at once. The very success of the standard hardened it into a constraint. The thing that made the network possible also set the ceiling on how fast it could ever change. You can see that ceiling clearly in a technology that should have been a revolution. It's called electronically controlled pneumatic braking, and instead of relying on a pressure wave crawling down a pipe, it sends the brake command electronically, so every car brakes at the very same instant. The results in testing were dramatic. In one pilot, a 100-car train running at 50 miles an hour cut its stopping distance by nearly 40%. In another, a heavy ore train stopped in well under half the distance it normally would. Faster, smoother, more even braking, with far less of that dangerous slack action. On paper, it solved the exact problem we just described. And yet it didn't take over. The reason is the same standard that made the network work. Retrofitting every freight car and locomotive in North America with new electronics, control valves, and connectors would have cost billions, thousands of dollars per car, tens of thousands per locomotive, adding up to a bill in the billions for the major railroads alone. Worse, the system only delivers its benefit if the whole train has it. Because cars constantly get interchanged between railroads, a train would inevitably end up mixing equipped and unequipped cars, and the moment that happens, the advantage evaporates and the fancy digital system becomes just another layer of complexity to manage. The railroads ran the pilots, measured the gains, weighed the cost, and reached a hard verdict. Better braking on paper wasn't worth the price and the incompatibility for a network built entirely on universal interchange. Once again, lower cost and simpler operations won out over a promising but expensive upgrade. Which brings us to the third reason, and it is the one that truly locks the empty car in place, and it has nothing to do with physics or history. It is the law. Under federal regulations, every freight train leaving its initial terminal has to pass what is called a Class 1 brake test, and this is no quick glance. The brake pipe has to be charged to a specific pressure. The pressure at the very back of the train has to register within a tight margin of the front. Air leakage has to stay under a strict limit, and a qualified inspector has to physically verify the brakes on every car. It is a thorough, time-consuming, federally mandated procedure. And here is the catch that changes everything. If you alter the consist, add a car, remove a car, even just rearrange them, the rules require you to do the entire test over again. Think about what that means for our empty car. Say a dispatcher is tempted to drop one empty hopper at a yard partway through the route. That single decision does not just mean uncoupling a car and rolling on. It means detouring the train to a certified brake test facility, recharging the whole system, rerunning every pressure and leakage check, re-inspecting every car, filing the paperwork, updating the consist records, and notifying the carriers, and the regulatory clock starts over from zero. Until that is done, the train legally cannot move. So a simple adjustment balloons into hours of crew time, idling locomotives, occupied yard space, and a ripple of delays for every other train waiting on that track or that crew. Faced with all of that, the math is brutally simple. It is almost always cheaper and safer to just leave the empty car exactly where it is than to trigger a brand new compliance cycle to get rid of it. That's the answer the title promised, but it's worth seeing how the money actually shakes out, because the numbers are not what most people expect. A mainline locomotive burns well over 100 gallons of diesel an hour, which is hundreds of dollars every hour it is running. But the weight of one empty car, maybe 30 tons against a train already hauling thousands, barely moves that fuel bill at all. The extra diesel to drag one empty car is almost invisible in the total. The real expense was never the fuel. It's the disruption, the crew hours, the yard dwell, the lost slot time on a busy main line, all the cascading delays that removing a car sets off. A single brake test can add a couple of hours to a crew's shift, and those hours cost far more than the trivial fuel penalty of just hauling the empty along. Railroads model these decisions over 15 or 20 years, not a single trip, and the verdict has been the same for generations. The cost of carrying the empty car is almost always less than the cost of tearing up the plan to remove it. So, if the logic is that settled, what's putting pressure on it now? A few things at once. The cost of every mile has climbed, fuel prices have trended upward for years, and crew wages have risen too, so each extra car, even an empty one, carries a sharper price tag than it did a generation ago. Communities along the tracks have grown far less patient with the noise and diesel haze of long, heavy trains, and their complaints have pushed railroads to rethink how long and how often trains run. And the industry's whole operating philosophy has tightened under an approach called precision scheduled railroading, which stopped obsessing over raw tonnage and started measuring everything by speed and efficiency, train length, how long cars sit idle, how fast equipment cycles through the network. Suddenly, every car is judged not just by what it carries, but by how quickly it moves. To adapt, railroads have leaned on some clever workarounds. They swap entire blocks of cars at key yards without breaking up the whole train, cutting the time spent reshuffling. They run unit trains, long strings of a single commodity going point to point that almost never need mid-route sorting. And they use distributed power, placing remote-controlled locomotives in the middle or at the rear of a train to balance those buff and draft forces and smooth out the pressure wave, which on some routes reduces the very need for an empty car at the tail in the first place. But none of these erases the underlying constraint. The moment you're dealing with a mixed train of loaded and empty cars, or an interchange partner whose equipment doesn't match, the old rules snap right back into force. The system adapts, but only in pieces, and for now the empty car still has a job to do. There's a human side to all of this that's easy to overlook. Real people are responsible for inspecting, maintaining, and safely running thousands of these cars, every one of them governed by exacting federal standards. A single brake test demands a detailed check of the pipe, the valves, and the couplers on every car, loaded or empty, with pressure readings and documentation that have to be exact. Crews are trained to catch a worn brake shoe or a slow air leak because one missed defect can cause a disaster miles down the line. They've learned through hard experience that shortcuts ripple outward, into delays, into safety risks, into extra work dumped on the next crew. And because freight cars stay in service for 30, 40, even 50 years, most of the fleet still runs on that same legacy air brake system and manual inspection, even as new sensors and digital monitors slowly trickle in. In a world where the stakes are measured in lives, cargo, and federal compliance, sticking to the proven routine isn't stubbornness. It's caution, earned the hard way. Can you really blame them? So the next time you're stopped at a crossing and you watch an empty car roll past in the middle of a loaded train, you'll know it isn't there by accident. It's the product of a brake wave that can only travel so fast, a 150-year-old standard too successful to easily replace, and a federal rulebook that makes removal more expensive than the ride. That empty car is a deliberate piece of insurance, kept in the train for the same reason you'd keep a spare in the trunk, because the cost of having it is small and the cost of needing it and not having it is enormous. Change is coming to the railroads, but it moves at the speed of trust and the slow turnover of steel, and for now, the empty car keeps rolling for a very good reason. If a thing you'd written off as pointless waste just turned into something that actually makes sense, that's exactly what this channel is built for. The hidden logic underneath the systems you pass by every day without a second thought. Subscribe and stick around, because the next one will do the same to something else you've never questioned.